Definitely got a lot chillier out since Wednesday, hasn't it?
Oh, okay.
Yeah, like Wednesday was like 70s, and then it just went straight down to 50. I'm like, what the heck? I was like, okay. Now it's like, I checked my phone this morning. It like went to below 30. I'm like 32. I'm like, oh whoa, okay. Now we're hitting fall weather, ladies and gentlemen. All right, here we go. Okay. So let's go ahead and get started. So the only thing I have in the way of announcements is, well, at least for now, Quiz 7 covers lessons 19 and 20, and opens up on next Wednesday at 9 a.m., closes on the following Thursday at 9 a.m., so yeah. The course coordinator put a little pinned note on Piazza to be like, okay, here's when the next few quizzes are going to be. And she said it goes up to quiz 10 in terms of, what the dates are and what they cover. So I would say just check Piazza for that. But other than that, does anyone have any questions on the homework that they want to look at right quick? Okay. So one thing I will do right quick is I did get a request on one of the first problems. So basically it was so let f of x equal, what did I have? So 2x squared plus 7x plus 5. And basically find concavity intervals. Let me write that a little better. So concavities, that way it's all one word. And inflection points. Okay, so basically what happens with this is that if you want to find the concavity intervals and inflection points, well, we got to find the second derivative of this thing. So basically what happens is that if you take the second derivative of this, well, what should you end up with as your second derivative? Okay, maybe let's take a step back. What's the first derivative?
4x plus 7.
4x plus 7, good. So then the second derivative should then just be a pretty quick application of power rule, is then just 4, right? So what you notice about this is that what this says is that for every value of x, this is always positive. For every x. So what should that tell you about the concave up intervals and concave down intervals?
Well, won't the concave up just be all the real numbers, so just be negative infinity?
Yep. So then consequently, since concave up is the entire real line, there's nothing regarding concave down. And then because it's always concave up, well, the concavity never changes, right? So what should that tell you about the number of inflection points?
There's none.
Nope, there aren't any, right? Right. Correct, there aren't any, is what I should have said. But, so, concavity doesn't change. So, no inflection points. So that one's just a pretty nice and quick one. So, okay, but other than that, that was it. So, any other questions on the homework you guys wanted to take a quick peek at? Okay. All right. So let's take a look at lesson number 20, which is absolute extrema on an interval. So for now, we are considering this closed interval a comma b. So what that means is that if we have a closed interval, that means we have to include the endpoints here. So both a and b in an interval. Okay, that's just all that means. Okay. So the absolute minimum is basically the lowest function value on the interval a comma b. And as you might have guessed, the absolute maximum corresponds to the highest function value on a comma b. So highest function value on a comma b. Okay. So as with we had a couple lessons ago, we had this idea of a relative extrema, which basically corresponded to a relative min or relative max. So in a similar fashion, we're also going to have that these two concepts are what are known as absolute extrema. So these are absolute extrema. Okay. Now the thing is that trying to find the absolute min and absolute max of a function on a closed interval is going to play out slightly differently than we had in the past, because before we could just consider the entire real line and then find relative extrema from that. But here we have to be a little bit careful with this. So for now, we're going to consider three curves on this interval a comma b below. So here's the x-axis, and here's the y-axis. I'm going to put a right here. I'm going to put a right here, and then b is going to go right here. Okay. The three curves are going to be considered below. So first one, so I'm going to put curve 1 right here. So curve 1, let me make sure I draw this carefully. So okay, so here's curve 1, curve 2, so curve 2, is here, and curve 3 is going to look something like this. Okay. All right. So if we take a look at these three graphs here, so what we're going to do is we're going to focus on what the absolute min and absolute max are of each of these. So let's start with curve number 1. So let's start with finding the absolute minimum of this. So what I'm going to do is I'm going to just go along the curve here and say, all right, well, what's the lowest function value? What's the highest one? So what you notice is that, well, if you look down here, what you notice is that down here we have basically sort of the lowest function value on a comma b if you look right here. So here, as a result, the absolute minimum is going to go right here. But then what you notice is that even though we have an absolute minimum on what appears to be a critical point, or a relative extrema, we also have that one of the other absolute extrema, which the absolute maximum, is actually right here, which corresponds to one of the endpoints. Okay? So just a quick little remark on that. So let's go ahead and do the same thing with the other two curves. So stop me, I'm just going to go along the curve here. So stop me if you hit either relative extrema and tell me which one it is. Okay? So with curve 2, let's go. Okay, where at? Okay, stop right there, and what kind of extrema? Okay, good, absolute minimum. Absolute minimum. Then someone else, stop me when we hit absolute maximum. Okay, good. Okay, absolute maximum. Okay. And then for curve 3, so let's do the same thing. Okay, we didn't have to start, which is good. Absolute minimum. And then stop me when we hit the absolute max. Good. So absolute maximum, right, goes right here. Good. Okay. So here's what that says. So it looks like, based off of what we're doing here, it looks like the absolute extrema can be either on one of the endpoints, as shown in curves 1 and 3, or it could be one of the critical points as shown in each of the 3 curves. It can either be something that we have a sharp turn at, or we could have just with the derivative equals 0. So absolute extrema can be either an endpoint or a critical point. So that's basically sort of the takeaway of what's going on here. So, okay. So as a result of this, if you want to find the absolute extrema, the idea behind this is the following. So first, find x values corresponding to an endpoint. And one thing to keep in mind is endpoint if included. If included, or a critical point, then plug each of those x values into f of x to find biggest / smallest. Okay? Okay, so once we do that, we can say, all right, well, whichever one's the biggest is going to give us the absolute maximum, and whichever one's the smallest is going to give us the absolute minimum. Okay, so give you guys a second to write that down before we get to our next example. So, all right. Okay. Everyone good? All right. So let's go ahead and take a look at the first example with this remark above in mind. So the first example states that we need to find the absolute extrema of 2x cubed minus 6x squared minus 18x plus 4 on negative to positive 2. So as per the remark, well, we already know what the endpoints are, and since they're both included, well, we're going to have to incorporate both positive and negative 2 into our analysis at the end of the problem. So for now, let's focus on finding our critical points. So step 1, find critical points. Okay. So as we've been doing up until this point, well, it looks like we're going to have to take our derivative to find our critical points. So a quick little application of power rule should tell you that the derivative is what?
— 6x squared minus 12x minus 18.
Good. Okay. So what you notice from this is that, all right, let's go ahead and try and factor this as much as possible. But here's the thing. These numbers look awfully big, so let's try and see if we can factor out something from each of these 3 terms here to see if we can make our lives a bit easier here. So what can we factor out of each of these 3 terms to make that?
6.
Yeah. So if we factor out 6, we have x squared minus 2x minus 3. And then you notice this quadratic here becomes much easier to factor. So if we do that, we end up with what two factors as our product? Let's have someone else answer.
Minus 2 and plus 1.
Yep. X minus, what was it?
2.
2?
And 3.
3, there we go.
And then
X minus 3, and then what was the other one?
x plus 1.
1. Good. Okay. So, the good news is that this is just a polynomial, so this is defined everywhere, so the only way we can get a critical point is if the derivative is equal to 0. So, this should pretty quickly tell you that the two critical points are going to be -1 and +3. But here's the caveats. So the thing is that if we were focusing on the entire real line, then yes, these would be the two critical points that we need to consider here. But we're not doing that, are we? We need to focus on the interval negative to +2. So that means we only care about the critical points that are inside this interval. So of these two, which one fall in this side of the interval? -1, right? So only x equals -1 inside -2 to +2. So we're going to have to disregard x equals 3. Okay? Alright, so now that we figured that out, that means we have to focus on, in terms of our analysis as per this above remark, we only care about -2, +1, and, -1 and +2. So, now moving on to step 2. So, plug each allowed critical points and endpoints into f of x, and then compare f of x values. F of x values. Okay. So, as per what we just said, the only values we can plug in are -2, f of -1, and f of +2. Okay? So now, all that says is, okay, now if we plug each of these three values of x into our original function here, then what do we get for each of them? So if we plug in -2 inside our function here, then if we plug this into a calculator, then what do we get for f of -2?
0.
Yep. So f of -2 is just pretty nicely 0, so that's good. What about f of -1?
14.
Yep, 14. And f of +2?
-40.
Yep, -40. Okay. So then, that should pretty quickly tell you that, well, of these three, 14 is the highest and 40 is the lowest. So highest is 14, and -40 is the lowest. Okay. And so because of that, well, that should pretty quickly tell you that we have an absolute max is going to be 14, and absolute minimum is going to be -40. And so as a result of this, what that will tell you is that we have an absolute maximum at the points, well, -1, and then the corresponding function value at that x value, so 14. And then we have an absolute minimum at 2, comma, the function value, -40. Okay? Okay, so that's example 1. So, any questions on that? Okay. All right. So now let's go ahead and do the same thing with example 2. So in this case, we have to find the absolute extrema of 6x times e to the negative x divided by 2 on 0, comma 3. So step 1, find the critical points. So the nice thing is that we just have 6x times e to the negative x over 2. So as a result of that, well, what should that tell you about the corresponding derivative?
Need product rule.
Yeah, you need your new product rule. Good. Need product rule. So what did you guys get for your derivative? So what's the derivative? Or should we, or does it seem like we should probably go over this one real quick? Okay. All right, so it seems like some people kind of forgot what's going on, so let's take a quick review of that. So in this case, with the product rule, remember, we have to take the first function times derivative of the second plus derivative of the first times the second. So in other words, we have derivative, let me write it like this. So we have 6x times the derivative of e to the negative x over 2 plus derivative of the first, so 6x, times the second. So the nice thing is that, at least with the derivative of 6x, well, that's just 6. So that's the second term is just this part. But what about the derivative of e to the negative x over 2? What's that going to be?
Is it negative 1/2 e to negative x over 2?
Yep. Because remember, chain rule is still a thing. So chain rule. That's how you get, so basically it would just be the exponential times the derivative of whatever's in power, essentially, for a chain rule, in this case. So here we have, all right, so ultimately we're going to end up with negative 3x times e to the negative x over 2 plus 6 times e to the negative x over 2. So this is going to be our derivative. So the nice thing is that, as with example 1, this itself is defined everywhere, so we only care about saying this equal to 0. So in this case, what would we need to factor out of both of these terms here to make our lives a bit easier here?
If you needed an negative x over 2.
Yep. So what was the first part?
Negative 3.
Negative 3, okay. Negative 3 to the negative x over 2. So in this case, we get x for the first term, and then minus 2 for the second. Okay, so if we set this equal to 0, that should pretty quickly tell you that x equals what?
Negative 6.
Negative 6? Okay, I agree with 2, but where are you getting 0 from? So remember, in this case, the exponential here, that's never 0.
It's 2.
Yeah, so it's just 2, right? Because if you plug in 0 here, you just end up with e to the 0, which is just 1, right? So the exponential is always positive. So more specifically, not only is it non-zero, but it's strictly positive. So in this case, the only one you care about is positive 2 here. So here, since that's inside our interval, that means this is going to be one of 3 points we have to consider here in step 2. So step 2, let's go ahead and plug that in. So we have f of 0, we got f of 2, and then we got f of 3. So if we plug in 0 back into our f of x that we had up here, well, the fact that there's an x factor here should pretty quickly tell you that f of 0 is just going to be a big fat 0. F of 2, meanwhile, well, what's the exact value of that? So we have 6 times 2 times e to the negative 2 over 2. So we have 12 times e to the negative first. And then in a similar fashion, letting x equal 3 gives you 6 times 3, 18, times e to the negative 3 halves. So the nice thing is that, like we said before, since the exponential is always positive, that should pretty quickly tell you that this 0 here is going to be the lowest. But which of these two is the higher one? Well, at that point, you're going to have to plug this into a calculator to figure out which is which. So I would say rounding to 3 decimal places, what are each of these two values here if we plug them into a calculator?
First one would be 4.415.
Okay, and the second one?
4.016.
0.16. Okay. So in this case, well, I'm looking at these approximations, that should be a bit clearer as to which one's the highest, i.e. the second one. So as a result, what that tells you is that we have an absolute maximum. It's going to end up equaling 12 times e to the negative first. And the absolute minimum is just going to be a big fat 0. So now what that tells you is that if you want to plug this into, or if you want to plug the point into long kappa, the absolute maximum is going to be at 2, 12 e to the negative first, because you want the exact value unless the problem says use a decimal approximation. And then the absolute minimum is going to be at 0, 0. Okay? Okay. So that's example 2. So, any questions on that part? Okay. So give you guys a second to write that down, and then we'll go to our very last example of the day. With like 20 minutes to spare, we have 20 minutes to do that. So hopefully we can probably get out early. So now here we have example 3, which is find the absolute extrema of f of x equals 6x squared divided by x plus 1. But now we have we don't really have a closed interval here, because with negative 1, 5, this bracket here denotes the fact that we are including x equals 5, but the parentheses says we're not including x equals 1. So brackets implies include x equals 5, but parentheses implies exclude x equals negative 1. Okay? So that's all that says. So So in this case, what you want to do is say, all right, well, actually, oops, there's a small little typo. So in this case, we don't want to find the absolute extrema of this. In this case, we only care about, not the absolute extrema, but in this case, we're just going to focus on the absolute minimum of this. Okay? And you'll see why in a second. So the thing is that in this case, we don't just have a nice little polynomial here. So we have to be a bit careful with how we handle this. So with f of x, we have 6x squared over x plus 1. So if we disregard the restriction on what interval we're considering here, what's the domain of the function?
Are real numbers except -1?
Right. Because remember, the only thing we have to be careful of in this case is dividing by 0 in the case of a rational function. So in this case, we want to make sure that x plus 1 is not equal to 0, or in this case, x is not equal to -1. But the good news is that based off of the interval we're considering here, well, -1 is not inside our interval, so we don't care. So not in -1, 5. So f of x defined in -1 to 5. Okay. So now, from this, let's go ahead and do our usual two-step process. So step 1 is, well, basically just find the derivative, since our function is defined on our given interval. So how would we take the derivative of this thing? So we're definitely going to need quotient rule for sure. Good. Quotient rule. Okay. So if we apply good old quotient rule to this, what do we end up with for our derivative? Go ahead.
So x plus 1 times 12x minus 6x squared times 1
Yep.
over x plus 1 squared.
Yep. So x plus 1. So yeah, low times d high. So denominator times derivative of the numerator. Then minus high. So the numerator times the derivative of the denominator. So just 1. Then all over the denominator squared. Okay? So now from this, let's go ahead and clean this up a bit. So if we do that, well, let's go ahead and leave x plus 1 quantity squared alone. So, because there's not much we can do with that for now. So if we factor the numerator as much as, or if we simplify the numerator as much as we possibly can, then what do we end up with for our numerator?
Is it 6x squared plus 12x?
6x squared plus 12x. Good. Because here, this is just, we have just 12x squared plus 12x minus 6x squared. Okay? And then let's also go ahead and factor the numerator as well, just to see what kind of simplification we get from this. So the thing is that if we factor the numerator as much as we possibly can, then what ends up happening? So if we factor this numerator, so if we factor out as many terms as we possibly can from the numerator, what can we get out of this?
6x times x plus 2.
Yep, 6x times x plus 2. Good. Okay, so now, let's go ahead and see what's happening here. So the thing is that, again, we have something in the denominator, so now we have to actually focus on where the derivative does not exist. But again, the derivative does not exist So in this case, the only way we can get the derivative to not exist is that, in this case, if the denominator were equal to 0. So as before, it looks like the only way that can happen is if we have if we're focusing on -1. But again, that's not in our interval that we're given, so we don't care. So ultimately, the only thing we care about here is when the derivative equals 0. So here, we have to focus on, if you want to figure out when the derivative equals 0, basically we have to focus on the numerator here. Because in this case, f prime is simplified as much as we can. Like, there's no common factors between the top and bottom, so we only care about the numerator here. So focus on numerator to see this. See this. Okay? So 6x times x plus 2 should tell you that the only two factors are or two x values are pretty quickly going to be, well, 0 and -2. Okay? But, so basically, of these three values, which one do we only care about here, given our interval? So basically, which of these are in the interval we're given here?
0.
Yeah, just 0. So, only x equals 0 in -1 to 5. So, only include x equals 0. Okay? So the thing is that now we say, all right, so with step 2, now let's go ahead and plug in the allowed critical points and the allowed endpoints into our function. So in this case, the only ones we can include are f of 0 and f of 5 because of the fact that, well, like we said, -1 is not included in our interval, so we only care about including putting x equals 5 into our function. Okay? So not x equals -1. Okay? So in this case, if we plug in if we plug x equals 0 into our function, well, that should pretty quickly tell you that x equals 0 yields what function value?
0.
Yeah, 0. And then for f of 5, what will you get there?
25.
Yeah, 25. Okay? So, in this case, well, that should, of these two, well, obviously the lower of these two is 0. So that should tell you that the absolute minimum occurs at what point? 0, 0, right? Okay. So that's example 3. So one thing you might be wondering is, okay, well, I figure we got 10 minutes, so I might as well answer this. So you might be thinking, okay, well, that's good and all, but why do we only focus on the absolute maximum of this? Or the absolute minimum of this? What's wrong with the absolute maximum? Well, here's the caveat. If I were to graph this, I'm going to plug this into Wolfram Alpha, because why not? So I'm just going to plug this into Wolfram Alpha to show you guys sort of what's going on. So 6x over 2 divided by x plus 1 on -1 to 5. So what you notice is that, well, the absolute minimum, as we just established, is at the origin. And then, but what you also notice is that if x approaches -1, because of the denominator down here, it looks like it's gonna keep getting bigger and bigger and bigger and bigger, right? So in this case, the absolute maximum actually ends up being sort of quote unquote infinity here. So for those in the online section, let me sort of show you what I mean. So I'll go ahead and give you guys the graph to show you what I'm looking at. So -1 and 5 goes here. So the graph is going to look something like this for those in the online section. So essentially, here's our origin. So the origin is our absolute minimum, so as we already established. But the absolute maximum, as you notice, well, what you also notice is that as x approaches -1 from the right, what you notice is that it ends up blowing up to positive infinity. What? Oh yeah, sorry. So we'll put this in terms of limits. Approaches 1 from the right of 6x squared over x plus 1 is positive infinity. So in this case, that's why we don't consider the absolute maximum here. Why we don't consider max here. Okay? So just a quick little remark on that, since I figured we got like, what, 10 minutes left, so this plus this last remark was the only thing I was going to mention. So let's go ahead and conclude with the mark, and you guys can get out of here with like 7 minutes to spare. So with problems like these, where you aren't given a closed interval a comma b, only need to find absolute minimum or absolute maximum, not both. Okay? So that's that. And that's basically lesson 20 in a nutshell. There we go. So any questions on that? Oh, okay, well, enjoy 8 extra minutes of freedom, and I will see you guys on Monday.